So welcome to everybody, and thanks for coming. Although we had to change the date due to an ongoing workshop. So what this lecture is about is essentially a kind of summary and a bird's eye view on what we have been doing during the semester. And feel free to interrupt me, ask questions, etc., as we move on. And it's meant as a very, very quick overview. And what we have covered this semester is actually quite a lot, although we moved a little bit slowly in the beginning because we looked at the review of neural networks. And then we went over to convolutional neural networks and recurrent ones. And we also had a discussion about autoencoders and principal component analysis. And this is essentially what we did before the Easter break. And then we moved into the kind of most important methods which are pervading the field nowadays. And these are generative methods. And we spent quite some time on energy-based models, variational autoencoders, and then the new kid in town, which is the stable diffusion models, which are some of the dominating models nowadays in, let's say, image generation. We also discussed generative adversarial networks, but we didn't discuss things like flow models, which we come back to a little bit later. The approaches which we have covered, they are approaches which deal both with supervised and unsupervised learning. We have not discussed reinforcement learning. That's something which is not covered by this course, but many of the methods which we have dealt with are actually used in both unsupervised and supervised learning. So, and then essentially what we have done is a classification and regression type of problems. We haven't touched much upon clustering, and the main reason for that one is that many of these models which we have looked at, or methods, they have often been applied to either classification or regression or both types of problems. As you probably have seen now, the topics which allow us to move into, let's say, uncertainty quantification is something which is offered by generative models, because in that case we define a probability distribution, and with a probability distribution you can actually quantify the uncertainties in your model. But we have not, although when we looked at the variational autoencoders, which carry also another name, which is called variational Bayesian inference. You can, if you want to, this is a field which we haven't moved so much into, you can develop a theory for quantifying the uncertainties in the parameters you optimize. But this is something which we haven't put a focus on. And so the machine learning theory we've been dealing with, together with the data analysis specific cases, are clearly linked often with the applications of the physical sciences. I should actually not put physics here, but I should put physical sciences, but this is a figure which I didn't change. So discoveries, fast simulations, and multi-scale modelings are common denominators for many of the things which we end up doing. So the focus here in this course has actually been on how we apply these methods to systems in the natural sciences, in particular the physical sciences. And there's been less emphasis on consequences of these methods for societal aspects, etc. This has been out of the scope here. And if you look at the whole plethora of machine learning algorithms, what we have focused on is essentially point number one. And this is where we've been living this semester. You also have methods like principal component analysis, which we used in order to motivate the topic like autoencoders here. And you can show that an autoencoder, if you have a linear transformation, is nothing but what you would have if you were to perform a principal component analysis, which essentially is you diagonalizing the correlation matrix. These other methods are covered in other courses, and we haven't dealt with them. method like 3, 4, and 5 are normally methods which we would call methods belonging to the pre-deep learning revolution. And linear regression has been with us since the 1850s. So that's close to 200 years. And we normally would consider that as a low-level machine learning method in its simplest approximation. Please just interject and ask questions. So when we look at these generative models, this is something which we brought up in the very beginning of the semester. That's a branch of machine learning that involves training a model to produce new data that is similar to a given data set. In practice, it means that we end up producing a probability distribution. And the simplest case to look at is the case of Boltzmann machines, which we discussed a little bit right after the spring break. And this is an image which I took from this textbook, one of the textbooks we have been using. And we would have some data we would train on, and then we have a generative model, and that generative model allows us then to generate new samples of horses. And if you look back just some few years ago, many of these generative models were not that good. So you would get humans with 10 fingers on one hand and or 3 hands and so on. But they have really been improved lately. And stable diffusion which is based on the diffusion model we looked at, is actually one of the dominating methods nowadays. But probably there will be many, many other ones coming up. So there's when you look back 10 years, this is what you might call archaeological times in machine learning. And so typically what you would require is a data set which consists of many examples of the entity you're trying to generate. And that's the training data. And then these training data are then used to generate a probability distribution. Let's see, there's a question in the chat here. Now, the class is actually in, we had to move, there's a question, it was a class. We had to move to the Center for Computing in Science Education. So we are in room 4, and this should be 6, 7. Just do that one. And if we just move on, I'm not going to say everything which you have here, but if we now link this with the discriminative models, which have been the type of models which you have encountered before. There's a typo here. The typical case then is that you would have some labeled data, and in this case, you're training a model which then can tell you whether this is a Van Gogh painting or not. And then you can train it and then test it on data which was not included in training, and then you can make a prediction whether it's likely to be a Van Gogh. And this is the basic difference between a generative model and a discriminative. So if you now look at the kind of taxonomy of these kind of generative deep learning methods, we have methods which we have covered, like variational autoencoders, energy-based models. We have looked at diffusion models. We have not discussed autoregressive models, which are the extension of recurrent neural networks. So we did discuss recurrent neural networks and long short-term memory methods, but we did not move on beyond that. This is actually a very hot type of models, which is particularly used in large language models, which we have not covered at all. And that's by obvious reasons, because we are actually more interested in applications to the natural sciences. And normalizing flow models are also models which we haven't covered. But then we also discussed generative adversarial networks. So if you ask me which of these are the ones which are more interesting for the natural sciences, I would say that the first 3 ones are, together with normalizing flow models, are those which are perhaps more interesting for natural science application. The books which we have used and where I borrowed a lot of material from are these 3 textbooks here. And then we have the standard one by Goodfellow, Benjo, and Corbin. So these books are more recent ones from 2021 and 22. But however, you will see that some of the developments there are even outdated nowadays. So I'd say sometimes it's very difficult to actually keep the pace. Any questions so far? Things you would like to mention, or which I have omitted in this kind of first general introduction? Then I just wanted to say a little bit quickly about the different methods which we have covered, so that you can have a kind of bird's view on bird's eye view on what we have done. Yeah, we have to room and define us. So I'm just going through what we have been following this semester, and neural networks is one of the entry points which many of you have seen before, and you have programmed that before. So since the group was pretty heterogeneous, I spent actually almost 3 weeks on that. And this is something, when I send you the feedback form, you can discuss whether this was necessary or not. The basic overview, because this enters also many of the other methods. The basic overview is that you have an architecture which consists of an input and an output layer, where the input layer is defined by the inputs, and then the output layer is given by the model result, and that is compared with a given target value. And you have a given number of hidden layers. The standard neural network is normally what you would call an affine transformation, where you essentially keep the dimensionalities fixed. There are ways to reduce the number of hidden nodes when you're running the calculations. And that is a typical method would be to reduce the number of hidden nodes randomly, so that you reduce the dimensionalities of the weight matrices. But in the most normal cases, I mean, what you end up with is a system where you have a purely affine transformation and a dense matrix of the weights and a vector for the biases. And then there is the discussion of the type of activation functions, and they may differ from layer to layer, although that's not common. And the last layer, normally called the output, has normally an activation function which is tailored to the specific. So this basic layout is also what you would see in a recurrent neural network and also in a standard convolutional neural network, except that then in convolutional neural networks, we would have filters which reduce the dimensionalities of the problem. And then there's obviously a cost or risk function or loss function, which is used to in the optimization part. And if you're having something like the mean squared error, you would also say that that gauges the quality of your model. But if you have other types of cost functions, this would not be the case. Some people train the absolute error. If you're doing a regression problem, it's quite common to have a standard mean square error. And if you're dealing with the physics-informed neural networks, you would often have the boundary conditions which are added to your loss function, which then are used to inform the system about the boundary which you're dealing with. So there are many here in this course who have actually written codes for physics-informed machine learning, which we haven't covered in much detail here, and where the applications to systems governed by partial differential equations is the main applications, and typically flow in fluids, or people dealing with the simulations of the heart have often simulated this through the applications of neural networks applied to partial differential equations, but where the physics-informed part comes from the boundary conditions and the initial conditions. Any questions so far? So this is just meant as a kind of review, because neural networks, which you see an example of here, they are also used in autoencoders. They are used as a basic start for CNN and for a recurrent neural network. They would typically be used in autoencoders, and you would also find them in energy-based models where people would use them instead of a model like the binary model, which we saw for Boltzmann machines. So neural networks, I mean, are kind of building blocks in many other type of methods. And typically the cost function, what we end up optimizing, this is the simplest case. This would be the mean squared error, which I've seen zillions of times. And I hope you don't get offended if I just remind you of that. And this would be the typical function which you would optimize with respect to these parameters theta. And theta is just a common container, a container which contains all the different parameters which you end up optimizing. And the neural networks, they are given by the so-called weights and the biases, as I say here. And another thing which, and I've said this always half jokingly, if you can improve any of these optimization methods, this is one of the places where you will get many new friends. And again, I'm not inferring that you don't have friends, but these are friends which will cite you. And Adam, I don't know if you looked it up recently, but the paper came in 2014, and I looked it up on Friday last week, and it has 185,000 citations. So a good paper in physics has 100 citations or something. Then most authors are pretty happy. So when you have 185,000 citations, so you get roughly 20,000 citations per year because the paper came in 2014. That's a lot. And that tells you actually how important the optimization part is. And this is actually you not cooking up a new optimization method, but actually finding a method to improve on the learning rate. So these are methods which then play a central role in essentially everything that we are doing. So whether we are doing variational autoencoders or stable diffusion models, there is always an optimization part. And being able to speed up that one by having better approximations to both the gradient descent and in particular this learning rate constant is a part of active and ongoing research. So in addition, there are tons of hyperparameters which you have encountered in different cases. So another thing I wanted to remind you of, since often these neural networks end as building blocks in many other methods, like autoencoders, then the universal approximation theorem plays a very important role. And let me just quickly remind you of that one. It simply says that you can approximate to a given error, a multidimensional function to an arbitrary accuracy. Exactly what this accuracy is something you have to play around with by experimentation. And assuming that the activation function for the hidden layers are non-constant, bounded, and monotonically increasing continuous function. So the original paper actually showed this by Sybenko or Sybenko, which I probably the right way of pronouncing that name. Was done with the continuous sigmoid function. And as you know, the sigmoid function is also one of these functions which led to a kind of, how to say, staggering in the interest for neural networks, because this function leads to the problem of both vanishing gradients in the training and also exploding gradients. And there was a paper in 2010 by Benjo and other ones, I think it's Benjo and Gloriot, which demonstrated that many of the deficiencies of the training of neural network was actually due to the application of the sigmoid function, which historically was the one which was used, and it was very much inspired by neuroscience, because it's a function where you can think when below a certain threshold it fires, it doesn't fire a signal, and above a certain threshold it sends a signal. And with this kind of deterministic function, what Sybenko showed is actually that you can approximate the function f of x here with a given neural network with one hidden layer. This theorem doesn't say anything about how many nodes you need. And it doesn't say anything about the general architecture of the network, many hidden layers. And that becomes just part of the experimentation. And then this was extended by Hornig by letting any non-constant bounded activation function to be included, using that the expectation value of this quantity here is smaller than infinity. And then you can actually show that this expectation value here is smaller than the specific quantity epsilon. So what this epsilon is something which you have to play around. So it doesn't tell you that the epsilon is 10 to the minus 10, but below a certain error. So as I say here, none of the proofs give insight into the relation between the number of hidden layers and nodes and the approximation error, nor the magnitudes of the weights and the biases. But what you could say is that they have a kind of universality, what function, no matter what function we want to compute. It doesn't mean that you can exactly compute any function, but you get an approximation that is as good as you want. And then it's you who decides what is as good as you want. And this class of functions is also, in a way, also used to discontinuous functions. And you could say simply, since the theorem is not applied to discontinuous functions, this is a case where you just try your luck. If it works, it works. So people have actually applied it, and it can function as an approximation, even if it fails sometimes. But you have to be aware of that for discontinuous functions, you may actually fail. So there is a set of Python codes here, which you can look up, and which you have seen many, many times, most likely. And this is also material which is covered in the precursor to this course, actually. And one thing I'm going to skip a little bit, because we also had that in the course on the physics SDK 4155. We discussed partly convolutional networks, but you will find examples of codes there as well. So what I wanted to say something about is more the material which was not covered in that course. So both CNNs and neural networks and RNNs are things which we have partly covered in the course. I know that some of you have taken these as well. So the part which would be new was the one about autoencoders. And that is a very popular method, and that uses, normally it actually uses a neural network. So an autoencoder, let me just skip some of this because this is just some of the repetitions here. The thing which is important for us is that an autoencoder splits into an encoder part, which maps the input via function fx, which takes an input x, which is your input variable, and then there is a set of parameters which you optimize, and this part could be given by a neural network. And then there is a decoder part, or a code part, or latent space, as it's also called. When we looked at variational autoencoders and Boltzmann machine, we call this a latent space. And this latent space is often a space which has a smaller dimensionality than the original X. So the output of this encoder gives us this latent space. And when we discussed the principal component analysis, when we assumed that this function was given by some linear transformations, you could actually show that the autoencoder is doing the same thing as a principal component analysis, which is a way to reduce the dimensionality. And then there is a decoder part, which actually maps these parameters back again into an output. And this takes this latent space as input, and there is a new set of variables which optimize. And this G could also be a neural network. Or if you're doing imaging, it could be a convolution neural network. So you could have a dense neural networks or convolutional neural networks, which reduce the dimensionality to a smaller space. And then there's a decoder part, which brings back a final output. And the typical goal then is to minimize the construction error, which is often then written in terms of difference between the output. So this function, let me see if I put it up here. Let me just go to dice. A typical construction error is actually the most typical one, is a mean squared error type of construction error. So this is the typical, so where you would have the input variables and then you have the output variables. So let me just say a little bit more about the autoencoders. So this is a typical structure. So you have some input and then you have some latent features and you reduce the dimensionality and then you bring back an output, which hopefully is as close as possible to the original. So as I said here, they are typically neural networks, which can easily be trained with existing software libraries. So the encoder can be written as a function g that will depend on some parameters, and where this h is the output of the encoder block. And normally this h is smaller or much smaller. That's the ideal than the original space x. So this function, the decoder and the output of the network can be written then as a second generic function, which is now given by this h of I as an input, where now you have this original g part, which does the encoding here. And then typically the function you want to optimize for these f's and g's here are then given by some difference between the input and the final decoded output. And typically standard setup, a feed-forward neural network, and that's normally called a feed-forward autoencoder. It has often an odd number of layers and is symmetrical with respect to the middle layer. And the first layer has a number of neurons, which equals the size of the input observation. And as you move towards the center of the network, the number of neurons in each layer drops in some measure. And the middle layer usually has the smallest number of layers of neurons. And the fact that the number of neurons in this layer is smaller than the size of the input is often called the bottleneck. So you can actually, if you look back at the image here, you can think of this as a kind of bottleneck. And you will see the same naming being used when you look at variational autoencoders, except that the variational autoencoder is you taking a probability distribution which transfers you from the input to a latent space. And this probability distribution is normally given by a known function so that you can calculate integrals analytically involving that known function, like a Gaussian distribution or binomial distribution. And that is then used to define a small latent space, which has a new probability distribution, which is often either uniform or Gaussian. And that is fed into the decoder, which then at the end gives you the final distribution. So that would be the difference between an autoencoder and a variational autoencoder. So variational autoencoder uses actually Bayes' theorem to do the encoding and Bayes' theorem to do the decoding. But the kind of philosophy is always the same. So you kind of overarching look you can take at all of these methods. I mean, that's my take on it, is dimensionality reduction. So I work in a field where we really suffer the problem of dimensionality reduction. When you do quantum mechanical many-body calculations, your Hilbert space grows quickly to levels which are just not tractable by standard methods. So anything which can reduce the dimensionality in a meaningful way, in a controlled way, is most welcome. But this applies to basically all of science. We always want to find a meaningful reduced space which represents the relevant degrees of freedom. So all of science, in my way, in the way I look at it, is you finding the right effective degrees of freedom, which are meaningful and which you can describe properly mathematically. So I'm just going to skip some of these things here. I'm not going to. So often the decoder part is something which mirrors the encoding part. So the network can actually look much the same, except that they are just opposite. And if you look back at this image, which you have here, what often happens in the construction of an autoencoder using neural networks is that the network you see here would be the same as the one you see, except that it starts with the opposite number of inputs to the decoder part. And then the output from the decoder part would have the same dimensionalities as your final data. And when you learn this representation, you have found an effective space here, which represents reduced degrees of freedom. So that was about autoencoders. The activation functions are often by the output layers. Since they are based on neural networks, the output layer plays a particularly important role, and the most used functions are often a real and sigmoid function. These are the most used ones. I'm going to skip some of these slides here. You can also do a binary cross entropy as before. If you're dealing with a classification problem where you have a binary output, if you have a case with more than a binary output, you would typically use a softmax function. But the softmax function is often limited because what you're doing then, if you have 10 outputs, the softmax would be so that if you have a value between 0.01, this would be the first one, and then between 0.1 and 0.2, it would be the second class, etc. So at a certain point, when you have too many classes, you would actually have to change the softmax with other types of functions, because then you would get very small errors. If you have 100, then you would have an output between 0 and 0.01, which would be the first class, and so you would move on like that. Reconstruction error is normally the metric that gives you an indication how good or bad the autoencoder was able, and the most typical reconstruction error is the mean square error. That's the most typical, as we said. Any questions? So that was roughly what we did in the first half of the semester, although we used a little bit more time on neural networks. So when you look at the feedback form, I'm going to send you a little bit later, because this course is under constant development, and there are methods which we have covered less and methods which we have spent a little bit too much time on. And I had a feeling that we spent a little bit too much time on repeating neural networks. And that has to do with the fact that the group is pretty heterogeneous, and there were people who had not studied machine learning before. So one of the things we will do next year is actually to have a prerequisite that you have studied some of these methods before, so that we can actually move on into the more interesting methods. Although I am not a big fan of repetition. Repetition is important. But these are the kind of, what I would say, the fun models. And this is the second part of the course. And we started actually with the family of Boltzmann models, or Boltzmann machines. And this belongs to the class of energy-based models. And then when we had that, we moved into variational autoencoders, which simply follow from these methods in philosophy. But the way we do the math is a little bit different, because for the standard Boltzmann machines, we don't use Bayes' theorem, whereas in variational autoencoders, you could actually use it. But these are more used in variational autoencoders, which are also named variational Bayesian inference. That's another name for the variational autoencoders. And actually, people who developed these came from the Bayesian statistics field. And then we have diffusion models, which are extremely popular. We also looked at generative adversarial networks, but we did not cover these methods yet. So with hindsight, what I could say is that maybe we should have spent more time on diffusion models and variational autoencoders. But I hope the lectures have given you the kind of feeling of what is the central part of these methods. Should we take a small break? Is that okay? Or should we just move on? What is your feeling? I mean, repeating and just putting things in a kind of quick and broad context is not always the most exciting thing, but the kind of idea is more to go through what we did during the semester and the choices of methods, and if there are other methods you're missing, because we haven't discussed reinforcement learning, we haven't discussed transfer learning, and some of these other very popular methods. And we have not touched upon large language models. And that's simply because we wanted to focus on applications to the physical sciences.
I was going to ask you a bit about because you mentioned a couple of times in discussing autoencoders and variational autoencoders that you can use them for causal discovery. Yeah, you mentioned a couple of times that you can use especially variational autoencoders for causal discovery because you actually get a sort of generative model.
Yeah.
So I was just wondering more about how you would kind of, because you're assuming that you're doing the dimensionality reduction first, so that the generative model goes from this low dimensional latent space out to the original feature space, which I'm assuming then includes both the sort of dependent and independent features, because obviously, question then is, how do you interpret that mapping, given that the low dimensional representation isn't necessarily in terms of the original features? So there's no point knowing the mapping function if you can't interpret the inputs.
So the mapping which you do is mainly done via known distributions, and you can think of the mapping as a kind of denoising of your original image, and then you reconstruct the original image through the decoder part. So
yeah, but so I guess with images it doesn't really make sense to talk of causal inference. But assuming you sort of have physical variables that you use as your original feature space, and then you reduce the dimensionality there, maybe there are some dependencies there that you make some of the variables redundant. But if you don't know how to interpret the latent space.
No, that's a very good point, because like if you look at the Boltzmann machine, which is the simpler case, you can actually give the latent space a simpler interpretation. And the latent space, if you make it equal to so the latent space is always a space where which you can think of as an aid. It brings in additional degrees of freedom, which allows you to optimize with more degrees of freedom. And then hopefully that one brings in effects and correlations which you did not have in the original space. So a Boltzmann machine here, if you just look at it, you can think of this H as equivalent to that space you start with. So if you're thinking of a particle in 2 dimensions, and you have 10 particles, this X would have a dimensionality of 20. So you have 2 spatial degrees of freedom and 10 particles. So you have your degrees of freedom is a 20-dimensional space. And then you could think of this H as being a kind of mirror image of that space. So you could have 20 hidden nodes. Then you haven't performed any kind of dimensionality reduction. And your latent space is just an aid for you to bring in some additional degrees of freedom in the optimization. So often if you have an optimization problem, if you have a larger space, the hope then is that you can give a better representation of the function you want to represent. You have more degrees of freedom to play with. But in general, this kind of latent space is not a space which you can think of directly as something which represents a meaningful physical representation of the system.
So how then would you use this for causal learning?
So the way you would use it is simply as an additional set of parameters, and you would have to play around and see how many of these you need in order to get the best possible representation.
So it would be more of a sort of black box simulation of the system than something that gives you a sort of symbolic representation of the causal structure.
So some of these methods, if you think of a dimensionality reduction with a principal component analysis, then you can actually make because your diagonal is a matrix, so you have an algebra problem, and then you can then say that some of these vectors are those, the eigenvectors you get are the most important ones. And they would be a linear combination of given features. And then you can say that, okay, out of 1,000 eigenvectors, if you have 1,000 by 1,000 matrix we diagonalize, there are only 10 which matter. And then you can give an interpretation of the system in terms of these 10 vectors. So that is a direct one. When you use an autoencoder, when you reduce the space, you can actually think in these terms. And you can make, if you tailor a variational autoencoder, so it looks like a kind of dimensionality reduction like this, you can then say that these latent degrees of freedom correspond to some specific components. So it's possible to do that, but it's a little bit more involved for variational autoencoders. But for the autoencoders, you can actually do that. So when you, and in particular, since this X tilde here is represented by a reproduction from a latent space, and you can show that the functions you're putting up, so this function which we called F here, and this function G, you can actually, if you now have a linear dependence on the unknown parameters, these weights and biases, then you can show that this is the same as using principal component analysis. So just to remind you quickly, a principal component analysis is you taking the correlation matrix, you diagonalize that one, and you keep only the largest eigenvalues. And these largest eigenvalues are the same as the variance. So when you sum it up, you can put a threshold and say that I keep 95% of the variance. And if this is represented by 10 out of 1,000 eigenvectors, these are the relevant degrees of freedom. However, these are not explicit degrees of freedom, because if you have 1,000 features and you diagonalize, your eigenvector is a linear combination of all the 1,000 features. But what could happen is that the first eigenvector is dominated by feature 1 with a coefficient of, let's say, 9%. And then there's just some small contribution from the other ones. So it's not a direct, I would say, link with a specific feature, in the sense that you have a linear combination of the features. So when you play around with, let's say, a Boltzmann machine, the simplest way you can look at this is just a space which gives you additional degrees of freedom in the optimization. For a variational autoencoder, on the other hand, since it mimics very much of what you have with the autoencoders, you can think of this as something which could be retraced to some physical properties of the system. But then you have to make that connection in the analysis.
So I guess I don't see how that is fundamentally different to just a regular feed-forward neural network, where you do have an input space and an output space, and you learn some mapping.
But a feed-forward doesn't give you a probability distribution.
Oh no, I guess not directly interpretable.
It's a discriminative model. Unless you use a feed-forward network to produce a solution of a partial differential equation. And then you can treat that solution if you do a quantum mechanical problem, if you square that solution as a probability.
Okay, so the idea is that you take the probability distribution in the decoder, which is directly interpretable, or like you get an analytic expression of it. Okay.
Yeah. So because when you have trained the final model, you have a probability distribution.
Mm.
So if you look at these Boltzmann machines, when I do training here, then what you get, because this is the full probability distribution, but what you want is actually this quantity which you see here, where you sum away the hidden space or the latent space.
Mm.
And this is the latent space or hidden space. They are just synonymous. They are degrees of freedom which you at the end you don't care about.
So you get the same sort of
Yeah.
input-output mapping, but you get additional information
Exactly.
by the network
Yeah.
part of the interpret.
So if you go back to coming back to this discussion of what the latent space means, if you think of the universal approximation theorem for a neural network, what that simply says is that you can fit a nonlinear continuous function to a given approximation angle. If you don't have a hidden layer, you can fit a linear function, but you cannot fit a function which is nonlinear in the unknown parameters. So a simple perceptron model can be used to fit just a straight line, but it would have serious problems in fitting function which depends on the variables powers of 2 or I. So that's another way of looking at it. So you can say you get additional degrees of freedom, which give you the possibility to fit more complicated functions and more complicated landscapes to optimize. But this, the function which you see here,
More complicated than the input space.
yeah, it could be. It could be. Yeah. Because your input space, I mean, your input space has just some. You may not know what your input space is. It comes from, right?
Yeah. But why would you want more degrees of freedom than in the system you want to understand?
So because if you think of an optimization problem, when you have a huge space, there is a larger likelihood, we can show that from optimization theory. There's a larger likelihood that you can actually get fit with the data, with the function you want to reproduce.
But okay, so presumably these degrees of freedom should correspond to some degrees of freedom in the target system.
Not necessarily.
So what are these additional, what do they mean, these additional degrees of freedom that you add in the model that aren't in the target systems?
Yeah, let's say, so for some of the methods, you have a straight mathematical connection. So if you think of parameterizing everything in terms of matrices, so you can always do that. And you treat that as a kind of Hamiltonian, then you know that if you have a linear type of problem, then diagonalizing the problem gives you a good approximation to it. And so if your problem is a 1,000-dimensional one, you can perhaps parameterize the eigenvalues, the lowest eigenvalues, with a matrix of dimensionality 5 by 5. That's fully possible. So you can construct a model which contains some matrices, which you then optimize with some parameters, but which are lower dimensionality. But how this links with a full problem, that's something which you cannot always dissect. So with a neural network, you cannot always dissect that directly. You can take this kind of matrix parameterization and apply that to an image as well. But then the so-called Hamiltonian you would fit would not be a linear combination of matrices, but it could be something which generates your conjugate gradient set of vectors. That's another possibility. That gives you another way of interpreting. But like these methods here, there is not a straightforward link with the degrees of freedom you add. So you have the possibility to rewrite things in terms, you can actually parameterize images. And we have actually developed a method which is called parametric matrix models, which does even better than any of the standard neural network methods on images, with just 1/10 of the parameters. And then you would use linear algebra to do the same thing. And that gives you interpretability. That's that goes beyond these methods here. So in a sense, you can think of this as just an additional feature you add to aid the optimization part.
Yeah, without any representational content.
Yeah. But the analysis of that one is something you can do in terms of often linear algebra methods. But they have often been less powerful than, let's say, variational autoencoders. or diffusion models. Should we take a small break?
Yeah.
And just stretch legs a little bit, bring back the. So let's. So when we look at the reason why I brought in the Boltzmann machines as well, is that they give a perhaps a more pedagogical introduction to the generative models. So the idea then is to train a probability distribution like this by optimizing this quantity. And the Boltzmann machine then, I mean, the nasty thing is actually in all these calculations is the training of the normalization factor, because that is in general intractable. And one of the examples which we looked at to show this intractability was to look at a binary machine where we had a function f, which deals with the input variables x as binary, and the hidden layers, or the latent space as binaries, which means that you have only two values. If you have m values for the input nodes and n values for the latent variables, this is the number of combinations which you would have. And even a small case like m equal to 100 gives simply an intractable function here. So when you're dealing with these kind of generative models, there are two basic things you want to, accomplish. You want to have something which is tractable. So that means that when you calculate this quantity here, it's something you can actually evaluate in a decent amount of time. And you also want to have flexibility. And flexibility in the sense that you can adapt to different data sets. So the Boltzmann machine in its traditional representation is not very flexible, because the type of functions you have here, which give analytical results for the probabilities and which makes the training easier, are not that many. So you have a binary Gaussian Boltzmann machine, and you have binary Gaussian and Gaussian, where you can calculate probabilities in terms of analytical expressions. And that makes the training often easier. So the bottleneck is the addition function or the normalization constant. And the way it's normally treated, suppose this x now represents a set of combinations of the x's, which then again we sum over the h's. So this is the probability, the marginal probability you want. Marginal because you sum away one of the degrees of freedom, which you're not interested in. This is the hidden one, or the latent space. And then you assume also that all the events are independent and identically distributed. And this is at the end the function you want to optimize, which means that you have an optimization problem, which is given by this problem here. Alternatively, you can take, and what is normally done is to take the log of that function, because you have a product here, and that's the equivalent problem. So this is what you end up with. And if you take minus log, you have a minimization problem. So whether you want to maximize or minimize. So most people like the minimization problem better. But this is a function you have to evaluate. And what we show then is that this function here, this one, in the optimization part, can be evaluated by what's called contrastive divergence. And what is done then is that you end up, when you now take this function, which you have, the probability distribution, take the log of that one, you have the sum over these minus the log of that. So what you end up with is this function here, which you want to set to 0. And the last one is then in the standard energy-based model. So this is the difference between an energy-based model and a variational autoencoder, is that we calculate it as it stands here. Whereas with a variational autoencoder, we rewrite these probabilities in terms of Bayes' theorem and define them a latent space, which supposedly is meant to have a smaller dimensionality than your input space. So this is a quantity which you would simply generate by summing over the data you have. So this is defined, you have defined a model. So this F is you having defined a model, you can define it as a neural network, like one of the examples we looked at. Or you can simply set up a simpler model, like a binary model, so-called energy-based model, where you then optimize the parameters, assuming that the hidden parameters and the visible ones are given by binary values. And then the marginal probabilities and the conditional probabilities are simply given by the sigmoid at the end. And that is much easier to implement numerically. But this quantity here, the one which you have here, this one is then evaluated by this expectation value here. And what you end up with when you have summed everything is now an expectation value log of this function, where x is now drawn by the model you have this defined, whereas this one is calculated with the data. So many people like to interpret these two things as a balance between you producing data or fake data. Some people like to make that analogy. And this term here is meant to correct the term which stands for the fake data. So this is these are the two quantities you end up with setting up. So this one, you can actually show that that's the log of that quantity. And this is what we went through. So this F, as I said, could be a neural network or just a simple Boltzmann machine. And the simple Boltzmann machine which we looked at was a binary, where you have made a model which is like this one. And that was the kind of model which was introduced back in the previous millennium. And since we are talking about archaeological times, it sounds better to say millennium than in the last 3 decades. So when you do that one, if you take this model here and you treat the x and h as binaries, let's say 0 and 1, then you will find analytical expressions for all the types of probabilities which are interested. And this will be your probability distribution in that case. And if you sum away or you calculate the conditional probability for h given x, then you can show that from this one you get a sigmoid distribution, since h can be 0 or 1. And the same with x. If you replace your model with continuous variables here, so you have x squared minus this a squared, then you get what's called a Gaussian binary. And then the conditional probability for x given h is a Gaussian. And these are probabilities which you can plug in easily, since you have analytical expressions. And that made the Boltzmann machines very popular, but they are less flexible. So it's always us trying to strike a balance between tractability and flexibility. So flexibility in particular, because you want this to involve some more complicated degrees of freedom than those which I have here. And tractability, if you make this more complicated, then the probability distribution you define and want to train becomes less tractable. So anything we end up doing is us trying to strike a balance between flexibility and tractability. And clearly, tractability and flexibility must also reflect meaningfulness. Yeah, I'm going to skip some of these here. I just have a list here of binary, and this is a typical Gaussian binary. And they all give you analytical expressions for the marginal probability and the conditional probabilities. There is also, as I said, a lot of hype now. And this is something which had escaped my attention because it came during COVID, which is a black hole in my life. I have to confess there are periods which I don't remember anything from. And I guess that applies to most of us.
Good choice of period to forget.
Yeah, exactly. But that actually escaped me. It came roughly in 2019, 2020, And in this case, the authors actually employ a standard convolution neural network on the MNIST data. And this does actually a pretty good job. So one of the things which we defined in the setup of variational autoencoder was this measure. This is actually a measure which is used to gauge the quality of a distribution. So P of X would be your ideal, the one which you think represents the data, and Q of X is a model you have. So this could be the encoder part of the latent space. And then you calculate what you see here, that this is an expectation value, because you have a probability and you're taking the expectation value of the probability divided by this model which you make. If these two are equal, then this is log 1, it's 0. So this quantity is a quantity you can show has to be larger or equal than 0. So it achieves its minimum when it's, or minimum 0, when these two probabilities are identical. And this is used then to rewrite the equations for the variational autoencoder. So mathematically, the autoencoder, the variational one, is actually also playing around with the product rule. This is the product rule of probability. And this is the function if you now have a continuous variable h. This is what you want. And here I'm suppressing all the parameters theta. So implicitly here there's a parameter theta, which you optimize. So this is the same as you wanted in the Boltzmann machines. This is the same you want in a diffusion model. All these generative probabilities, they obviously rely to you being now able to find x generated by P of X. So when you see a symbol like the one which I put up here, this means that x, which you see here now, which enters here, is generated by this model, which you have. Whereas here, it's your data. So essentially, what a variational autoencoder is us playing around with this term here, but introducing a new probability distribution and using Bayes. So what you do then is to include a new probability. And this is a conditional probability, which is probability of h, your latent space, the reduced space, given x. And this has some parameters. And these parameters are normally given by the mean value and the variance for Gaussian, or any other type of distribution you want to use. But the whole thing is that you have something which is tractable. So again, tractability and flexibility come to play. So this is a flexible variational distribution. So you vary the parameters with parameters theta that you want to optimize. So you can think of this as something which can be parameterized, that is learned to estimate the true distribution of the latent variables for given observation sets. And it seeks to approximate the true posterior. This is a true one, if that exists. So that's your, so the way you're rewriting the equations is assuming that there is a true posterior which maps into that space, and you want to approximate that with a function. So this is perhaps coming back to your question about what is the true representation of the posterior. So this is something. Oops, maybe I should switch to the. Let me switch to the Jupyter notebook for some of these things here. That gives a better. See, the Jupyter notebook. I have too many windows here. Just try. Let me just find my proper one here. There we have it. So let's switch to the Jupyter notebook because there are some equations which are a little bit more, which are easier to see in the notebook than in the slides there. So if we scroll down, we have these equations which you see here. Let me squeeze them down a little bit. So if you look at the equations, what we optimize is this quantity here, log P of x. That's the one we want to calculate the derivatives of. And in this case, what you have is a series of manipulations which are actually brought in. So you would simply plug in 1 because you assume that this is normalized. So I'm just multiplying with 1 here. This is an integration of h, so P of x is assumed to be independent of h. So this is just a marginal probability. So you can rewrite it like this, which again means that this is nothing but an expectation value with respect to this probability, which you make a model. So then what you have is this quantity. And then you can rewrite that one using if you go back here, this is just playing around with the standard probability rules. So this probability of x is given by the probability of x and h multiplied with the conditional or the divisor. So these are just playing around with this kind of so-called chain rule because you can rewrite this px of h. This is the probability you have, which describes both the latent space and the visible space. And that can be written as a probability of x given h multiplied with p of h, or probability of h given x multiplied with p of x. So these are just some of these basic rules which you will find if you take a course in statistics in the very, very beginning. And Bayes' theorem, which plays the same role as Pythagoras in geometry almost, is just as simply us using this chain rule of probabilities. And then what you do, you use the chain rule of probabilities and you have that one. And now you're soon ready. So you just multiply with 1 again. And you have this equation here. And you can split this since you have the logs of the probabilities. So you would have the log of px of h, the probability, divided by this conditional one, plus this quantity here, which is nothing but this Kullback-Leibler divergence, which is larger or equal than 0, which means that this quantity here is larger or equal than this expectation value. This is also called in the literature as the evidence lower bound. You will often find that one. And this follows a default formulation by Kingma and Welling, which introduced the variational autoencoders back in 2015. So you can rewrite it, and you have a first term, which is given by this one, plus this term, and these are the terms you want to optimize, where you take the derivative with respect to the parameters. So that these are the ones which lead to the x. So you, instead of solving these equations which you saw here for Boltzmann machines, the so-called contrastive divergence, now you're actually optimizing by taking the derivative with respect to the parameters, you're optimizing these two terms. And this term here is normally seen as the encoder point, and then the next term is the one which brings you from the latent space back to the final output, which is your model representation. But then these expectation values are generated with a probability distribution whose model you have defined, and that can be typically a Gaussian. So the two terms, they have some kind of intuitive description. The first term measures the reconstruction likelihood of the decoder from the variational distribution. And that ensures that the learned distribution is modeling effective latence that the original data can be regenerated from. And the second term measures how similar the learned variational distribution is to a prior belief over latent variables. So that prior belief is something where you also have to plug in the model. So everything you see here is just us. If you look at this equation here, this is just us. When you look at this one, this is just us using here Bayes' theorem and the chain rule of probability. And then there are different ways of actually dealing with that. So you can, this is normally the Q is normally represented by a normal distribution. And the prior which you have for the latent space is also given by a normal distribution. And these are the parameters which you then want to vary. So you don't vary the distribution, but you vary the mean value and the variances. And you have also defined, in principle, there should be a covariance here, but you actually made the covariance diagonal to simplify the calculations. This is a standard setup for a variational autoencoder. And then we have the diffusion models. And in the diffusion models, as I said, one of the things you want to attack is the flexibility. You want to have a flexible distribution, but you also want it to be tractable. So these two keywords, tractability and flexibility, they pervade everything we do with machine learning. So it's you actually at the end who has to strike the balance between these two major issues, tractability and flexibility, and see which is the method which applies best to your data. So the diffusion models, they have some advantages over the other methods, and that's a claim by the authors: extremely flexible in model structure, exact sampling, easy multiplication with other distributions, and also the model log likelihood and the probability individual states can be evaluated cheaply. So you can think of a diffusion model as a set of stacked variational autoencoders. That's the simplest way to think of the original setup. And in that sense, the way you can think of it is you actually taking many encoders. So here my latent space, because I borrowed this figure from this article, so they define the latent space with Z, whereas I've kept H. But then you have probability distributions which bring you from the original data by setting up a Markov chain. So you're using the theory of Markov chains in the sense that you can actually set up products of, so you have the probability of moving from one state to the next state. And you assume then that when you repeat this, this is independent of what happened before. And then you can simply multiply these probabilities in terms of chains of probabilities. That's the Markov part of it.
Yeah, just a question on this. You've been talking about burning period and steady state, right?
Yeah.
So qualitatively, what does it mean? And does it mean that when you reach this steady state, then the chain becomes Markovian? Is that correct?
That is the assumption.
That's natural, okay.
But then your transition probability has to be a stochastic matrix, which converges to one state with the largest probability.
Yes. And when you reach this state, you can sample.
Yeah.
And in this burning period, what's happening?
In the burning period, I mean, you start typically randomly.
Okay.
And depending on where you start, it can take more or less time to reach the most likely state.
Okay.
So the most likely state is the one which has, which corresponds to the largest eigenvalue of a stochastic transition matrix.
Okay.
If you can think of everything as a stochastic matrix, which is multiplied with the original state, which you can think of as a vector, and that transfers you to a new state.
Yes.
And then you keep repeating this. And then at the end, the states which you started with is equal to the state you end with. So your final state becomes time independent.
Yes.
And that's the most likely state, or the equilibrium state, or the stationary state. Same name.
Or steady state.
Yeah, or the steady state.
Okay.
But if you have degeneracies in the stochastic matrix, then it can oscillate between different states. And then it may not converge to the most likely state. That you don't know.
And because I'm trying to play with diffusion model for the project, and you have to define it's a hyperparameter.
Yeah.
It's called the time step.
Yeah, exactly.
And so in relation to smart Markovian, what does that mean? And if you increase it or not, then
so that becomes, as you said, a hyperparameter, which enters your Gaussian distributions. Because these Qs are actually Gaussian distributions. And the only thing you change is then obviously the steps, because you change perturbatively. So you could think of you changing here small steps, the mean value and the variance. These are the parameters we change. Your probability stays the same. And that's what gives rise to analytical expressions. Actually, this paper here has all the derivations of all the quantities you're interested in, if you look it up. So I didn't go into that in much detail last lecture, because if I'm going to, when I redo this course, I will actually put less emphasis on neural networks, because many of you had seen that before, and rather spend more time on the mathematics here. Because I think that's a little bit more interesting. That will be also more new for people. But this article has all the mathematical details. And it's a very nice article because it shows the link between variational autoencoders and diffusion models. So what this would be, this would just be a stacked autoencoder where you simply play around with the product rule of probabilities. So you start with some additional data. You have a decoder, new decoder, and a new decoder, sorry, encoder. And then you reach a final step T, and this will depend on the stepping size. And then you reconstruct it. So you start with an image, and then you denoise it, and till the end you just have plain noise. And then you reconstruct it through simply a repeated applications of these products of probabilities. So the definition, so here in this case, the equation you end up with is actually this one. This is the one you want to optimize. But then in variational diffusion models, what you say is that the latent dimension is exactly equal to the data dimension. The structure of the latent encoder at each time step is not learned, it is predefined. A Gaussian, for instance, or binomial distribution, or whatever. And then, in other words, it's a Gaussian distribution centered around the output of the previous time step. And the Gaussian parameters of the latent encoders vary over time in such a way that the distribution of the latent at the final step is a standard Gaussian. So you simply end up with the products of Gaussians, and what you would set up then would be this alpha t here. This is the way you would set up the mean values in terms of the previous one. And then you have a variance like that. And then it's alpha t becomes a hyperparameter.
So the longer the chain, the better the reconstruction.
Normally. Yeah. So I'm just not repeating it, but you can schematically, you end up with a kind of denoising or noising of the figure, and then you reconstruct it here. And these models have been proven to be extremely efficient. So this is just the basics, but then you have the additional training elements which we didn't discuss in more detail, So we put up the different terms which you end up with. These are the different terms which you need to optimize in the calculations. So it gets more complicated. So we have a discussion of GANs as well below here, but I guess I'm gonna skip that one. You can just take a look at it if you want. I find the GANs perhaps less interesting than the diffusion models, also because the diffusion models are closer to the way I would think of training a given model.
Okay. I think GANs are quite intuitive in a way that.
Yeah, they are. Yeah, I agree. Yeah, I agree. So many of these models I don't know that you are using in your research. I mean, you said you were trying to implement diffusion models.
Not implemented,
Yeah.
they use them, not understand what it's about
Yeah.
because it's
Yeah.
complex. So
Yeah.
the parameters and all.
So what kind of problem will you be applying them to?
It's image generation
Right.
for satellites. So it's a 300 million parameter. So I'm using pre-trained models